Okay, so I am going to introduce to a topic in software testing, which we call graph coverage criteria. And in this topic, we estimate what sort of structural elements are covered in a graph by means of certain test requirements. So I will be making use of slides by Professors Paul Aman and Jeff Oppert, and these are actually available on this link, which you can follow if you want a copy of these slides. So let's begin. So basically, graphs can be extracted from several different input sources, and one of them can be the source code, which is going to be the focus of today's lecture. It can also be extracted from different sort of specifications, which we write either in natural language or more precisely in formal specification languages. And we can also extract the graphs from design artifacts used in software engineering. And likewise, we can also construct a graph model of use cases in which we often specify which use case, for example, is extended from another use case, or which use case is included in the description of another use case. So these can serve as the connecting points between different use cases and serve as the connecting edges in the case of a graph which we want to extract from that particular artifact. So graphs are the most commonly used structure for software testing, especially in the context of white box testing, and these can be coming from many different sources, as we just saw on the previous slide. And the graph which we use in this case is called a control flow graph, which is basically extracted from the source code of a program, and in that case it just captures the flow of control from one point of the program to another point in the program. And the flow of control basically can vary when we have branches or loops or nested loops or nested branches in the code that can result in the flow of control from transferring from one point to another point in the program. Similarly, we can also extract graphs from these design structures. So design structures also provide a good estimate which sort of structural elements are connected to other structural elements of a particular software in terms of its design. Another very good aspect of a graph are the finite state machines or state charts, which are also used in software modeling. So these can also be used to provide the structural representation and how those components in the structure are connected with one another in the form of a graph. And similarly, as I just told you about the use cases on the previous slide, these can also serve as creating a graph of a particular software. So in this case, tests are usually intended to cover a certain portion of the graph, and we would like to cover certain elements of the graph which we can recognize by just looking at the graph, like whether we are covering a specific node or a set of nodes or some edges, or maybe a pair of edges, or maybe a set of or a combination of edge pairs and so on, and what sort of for example loops we want to cover. So these are several aspects which we can consider when we are doing white box testing. So let's go quickly through the definition of a graph. So what we mean here is a graph is basically consisting of a set of nodes, and another restriction on the set of nodes is that the set of nodes cannot be empty. In the same way, the set of nodes must have a set of initial nodes, and the restriction on this one is that it is again not going to be empty. And the set of nodes must also have a set of final nodes, and the set of final nodes must not be empty. So these are the must constraints on the nodes of the graph, that it must have one or more initial nodes, one or more final nodes, and it must have a set of nodes which must not be empty. And in the same way, these nodes have to be connected with one another in some way, and the mechanism that will be used is called an edge that connects one node to another node and in this case an edge will be a pair. For example, you can see here that Ni and Nj are two nodes which connect each other. In this case, we will call I as the predecessor node and J as a successor node. So here we see an example graph, and here we see that the initial node consists of the set of initial nodes consists of this node 1. This incoming arrow is telling us that this is an initial node, and there is no more edges going out of this or into this node, and this bold faced edge or the boundary of this node is telling me that this is an initial this is a final node, and there are no more nodes connected to this node. So we didn't impose a restriction on the edges that the set of edges is to be it must not be empty. So this is a valid set where the set of edges can be empty. We have a set of nodes that just has one node. We have a set of initial nodes that has one node. We have a set of final nodes that has one node. So if we question whether this is a graph or not, so yes, in fact it is a graph because it fulfills all these conditions we just saw on the slide. So here we have some other examples of the graph. In the first case, we see that we have four nodes, and these four nodes have this initial node and this final node. This bold boundary of this node is telling us that this is the final node. And if you look at the first one, this is the initial node. It means the condition of the initial node is fulfilled. The initial node set is not empty, and likewise the set of final node is not empty. So the two conditions are fulfilled, and the set of nodes in fact is also not empty. Therefore the three conditions, necessary conditions which were required for the construction of a graph are fulfilled. And here we can see that we have this edge 1 to 2, then we have another edge that connects node 2 to 4, and another edge that connects node 1 to 3, and another edge that connects node 3 to 4. So we can see that the set of edges has these four pairs, which shows the connection between these four nodes, how these are connected to each other. So therefore this depicts a valid graph in this case. Another example you can see on the right is this one. Here you can see that we have 10 nodes in the graph, and 3 of them are initial nodes. So it is possible that a graph has multiple entry points, and in the same way it has 3 final nodes. These bold edged boundaries are telling us that these are the final nodes. And so in this case the set of initial nodes has 3 nodes, and the set of final nodes has again 3 nodes, and the set of edges has these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12 pairs of edges. So the set of edges are 1, 4, 1, 5, 2, 5, 3, 6, 3, 7, 4, 8, 5, 8, 5, 9, 6, 2, 6, 10, 7, 10 and 9, 6. So this again is a valid graph. And now if I look at the structure shown on the right side of the slide, here we can see that there is no initial node. We don't have an incoming arrow to any of the nodes in the graph. So in this case the set of initial nodes is empty, which does not fulfill our condition for a valid graph. Therefore this particular structure shown on the right of the slide is not a valid graph because the set of initial nodes is empty.